Hi, so welcome to Math140, Calc 2. This is lecture 16. And what I want to do today is, the last of the lectures on partial fractions. I think we'll all be happy when we get past that. And then I want to talk a little bit more about new substitution. I want to talk a little bit more about U substitution and just do some of the standard practice problems. So again, I've got the list. We've done some of these integrals already. We'll do a few more later today. So for partial fractions, we need a few things. One is remove multiples of denominator from the numerator until the top has smaller degree than the bottom. So again, if we have a degree 4 polynomial down below and a degree 8 polynomial above, we can use polynomial long division as much as we love it, and you remove some multiple of the denominator from the numerator and then look at the remainder. And the remainder will have smaller degree. So it's sufficient to study things of the form, g of x over f of x with degree of g less than degree of f. We only have to be able to do cases like that. Step 2 is factor denominator. Say it's maybe f1 of x to the r1 dot 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 fk of x to the rk. So we have different degrees. And then we do a partial fraction expansion. And then we write g of x over f of x as, and this is where the notation becomes a nightmare. I'll just do a sum. L goes from 1 to k. And then we'll have a sum. M goes from 1 to 1, we'll have f1 of x to the degree m. And then we'll have here a polynomial of degree 1 less than fk. I guess we're doing f. So what are we doing? So we have a double sum. So the sum over L goes from 1 to k. That just goes for each of the factors we have. Look and see how it comes into play. So we do it factor by factor by factor. And then for a given factor, we could have FL to the first power, to the second power, to the third power, all the way up to RL. And then the numerator is a polynomial of degree 1 less than FL. So this is what we've been calling the base polynomial. So here, this is like the base polynomial. It's much easier to just see this in an example in practice. So again, this is the messy formula. It's really better not to memorize this and just say, okay, well, when I have something in practice, let me just do the expansion. And as I do the expansion, it becomes clear how to do it. The harder and harder things are, the more you have to ask yourself, why am I doing this by hand? Right? Anything that's truly horrible, you will use a computer program to do. But you should know enough that you can do some basic ones by yourself. There are times in advanced math and science where partial fraction expansions actually play a role. One of the ways to find a closed form expression for the nth Fibonacci number. So who knows what the Fibonacci number is? Anybody know the Fibonacci's? 1, 1, 2, 3, 5, 8, 13. Each one is the sum of the previous two. If I told you your entire grade depended on calculating the millionth Fibonacci number, would you be happy? It's just addition. How big of a deal is it? Well, you can try to figure out just how long would it take you to do 1 million additions. If you had to do this by hand, I'm not so sure. You can start doing some calculations. You know, how many seconds are there in an hour? Seconds in an hour. Come on. 3,600, right? So how quickly do you want to say you can do a calculation? The numbers are going to start to get really huge. You want to say you can do it. How long to do? A million additions. So as an exercise for extra credit, try to figure out just how many digits would you have to be adding? How long would it take you? If you had to do this by hand, you want a ballpark estimate. How big is the millionth Fibonacci number? Do you think it has more than a million digits? Do you think it has more than 1,000 digits? Roughly, and make some estimates as to how many digits. Each Fibonacci number is about 60% of the previous. And so you can actually just calculate. There's a closed formula which you can get using partial fractions for the Fibonacci numbers. And so I will just calculate the millionth Fibonacci. Good. So here's the millionth Fibonacci number. Goes on for a while. Okay. Does that mean anything when you see something that large? So let's get some sense of how large it is. So let's take the log of this base 10. I have to put a 10 point so that it knows to give you this. Oh, okay, so it goes in the other direction. You do the base first. So the log base 10. So it has a little over 200,000 digits. So even if you're just looking for the last couple ones, you've got 200,000 digits. And so you can estimate how long would it take you to do all the additions starting from the beginning. It turns out that there is a formula that allows you to jump to whatever Fibonacci number you want. And the way you prove that is using partial fractions. So it is a useful technique, but as the problem gets worse and worse and worse, you're not going to be doing it by hand. So let's just go back and talk about if we had a factor of 1 over x to the n, we'd have a over x plus, let's say a1 over x plus a2 over x squared plus a3 over x cubed plus dot 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 plus an over x to the n. And so this is the simplest possible denominator I could have, is the x every single time. And if I combine that, what do I have to multiply the first one by to get a common denominator? X to the n minus 1 over x to the n minus 1. So I'd get a1 x to the n minus 1 plus a2 x to the n minus 2 plus dot 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 plus an over xn. Notice the numerator is an arbitrary polynomial of degree n minus 1, one less than the denominator. So again, this is not a full proof that we only have to use one less than the base. So for the x cubed, I don't have to write something x squared plus something x plus constant. I don't have to do that. The reason is the other terms can absorb that. And we saw that the last time. If I write something like this, this is general enough to get anything. Okay. And so we can reduce to basically 1 over x, or 1 over x to the m, then 1 over x squared plus 1, and 1 over 1 minus x squared. Basically, or I guess 1 over x squared minus 1. We can essentially reduce things to being one of these. And that's it. Now we've reduced it to something we know. Now you have to remember things. So you have to remember, if I have 1 over x squared plus 1, what function has derivative 1 over x squared plus 1? Arctan. So that's worth remembering. If I give you 1 over x squared minus 1, well, I could actually write this as 1 over x minus 1, x plus 1, and that's telling me use partial fractions for that. If I have 1 over x to the m, what function has derivative 1 over x to the m? So I want a function that has derivative 1 over x to the m. Or I sometimes find it's easier to write this as x to the negative m. So what function has derivative x to the negative m? Let's start with 1 over x. What function has derivative 1 over x? Okay, natural log of x. So if we have a 1 over x, we know it's natural log of x. What if I have a 1 over x squared? What function has derivative 1 over x squared? X to the negative 1. Almost. Almost. You have to be careful because you have to worry about if I have x to the negative 1, I take the derivative. I got negative 1 x to the negative 2. But you're correct up to a constant. So we can fix that. So if I have to find the antiderivative, what I always do is I always get the exponent first, and then I fix whatever I need in front of it. So if I want, the integral of x to the negative m dx, well, it should be, when I integrate, I increase the exponent by 1. So it should be x to the negative m plus 1. But when I differentiate, the negative m plus 1 is going to come down. So I then have to correct and divide by negative m plus 1. So this is how I always find the antiderivative of something like x to the negative m. I know that when I differentiate a polynomial, the degree goes down by 1. When I integrate a polynomial, the degree goes up by 1. So I'm going to start with, I know it's something x to the negative m plus 1. I just don't know what that constant coefficient is. Well, when I differentiate x to the negative m plus 1, it's going to get a negative m plus 1 coming down. So to kill that, I have to have a negative m plus 1 in the denominator. And this would be the antiderivative. So this is how I would find the antiderivative. What's the one case I have to be careful about? Good, so what value of m do I have to worry about? Negative 1. But although the way I've got things written, it's not negative 1, it's m equals 1. But yes. So this is if m is not 1. And the integral of x to the negative 1 dx is just the natural log of x. And the integral of 1 over x squared plus 1 dx is arctangent of x. So these are our building blocks. The goal is whenever I give you an integral, reduce it to something like this, and then we'll be in good shape. So let's consider a problem. So let's say we have x squared, x plus 1, 3x to the fourth plus x minus 2 dx. So I am being extremely kind and factoring the denominator. Why am I being kind and factoring the denominator? I notice nobody's yelling because you're a kind person, Professor. I'm the one at the blackboard. With the COVID policies and whatnot, in previous years, I would have actually split people up into the blackboards and said, okay, you guys go to this one, you guys go to this one, everybody do a problem, and then present it. Right now, I'm not sure if I'm supposed to be having people moving around in the room, so since I'm the one here, I will just give it to you already factored. If you do not remember how to factor polynomials, it becomes a bit harder to use the method of partial fractions. Maybe I'll talk a little bit later today if we have time about how you might factor. But this is really the same as the integral of 3x to the fourth plus x minus 2 over x cubed plus 1 dx. So what's the first thing you would do? Yeah, we have to do some division because the numerator is greater than the denominator. So we have two ways to do this. We could do polynomial division, we could say I have 3x to the fourth plus 0x cubed plus 0x squared plus x minus 2. And I've got x cubed plus 1, and I can do it out like that. So that's one way to do it. Yes. Oh, sorry, it's x cubed plus x squared. And so I could, do it out like that. Right. Another thing I could use is, well, I've got 3x to the fourth. That looks like x cubed plus x squared times 3. So I could just start by doing like 3x to the fourth plus x minus 2 is 3x to the fourth plus 3x squared minus 3x squared. I'm sorry, I want x cubed. Minus 3x cubed plus x minus 2. And the reason is the first piece now is just 3 times the denominator. So if I do that, I would get my integral is equal to the integral of 3x x cubed plus x squared over x cubed plus x squared dx plus the integral of negative 3x cubed plus x minus 2 over x cubed plus x squared dx. And now what's the first integral going to be the integral of? Yeah, just 3x dx. And what function has derivative 3x? Sorry? Almost. So 3x. What function has derivative 3x? Perfect. So it's just 3/2 x squared. And then we would move on and we could play the same game with the next one. I'm essentially doing polynomial long division without writing it out formally. So if you really, really hate polynomial long division, here's a way to just bypass it. And now I've got the negative 3x cubed. Well, that looks like negative 3 times the denominator. So I would need a negative 3x squared, so we then have to add a 3x squared. Okay? Does everybody see how we can go about this in either one of two ways? You can either do polynomial long division, or we could keep playing this game. I could then write negative 3x cubed plus x minus 2 is negative 3x cubed minus 3x squared plus 3x squared plus x minus 2. And then when I feed that in, I would then be left with another thing that's easy, and I would have 3x squared plus x minus 2 over the denominator. And again, if I had done the polynomial long division, I would have gotten these multiples as well, and then I would have gotten the remainder of 3x squared plus x minus 2. So we now are down to, we have to integrate, I think it was 3x squared plus x minus 2 over x squared, is it x plus 1? So we want to write this as something over x plus something over x squared plus something over x plus 1. So what is the numerator going to look like for the x term? Sorry? Wait, but I'm saying we then handled the first part of it, right? We handled the first part, and then we reduced to this over here. And then we said, well, actually, if I add in negative 3x squared plus 3x squared, I would then get negative 3 times the denominator. So that would be something that I could handle as well. And the only part that's now hard to handle is the 3x squared plus x minus 2. So we just have to handle that part now. And so what are the possibilities for the first factor over x? What's the possibility? What degree polynomial will it be? In the numerator. Sorry? I think I heard the answer over here. 0, right? X has degree 1, that's the base polynomial. So the numerator is polynomial of degree 0, so it's a constant. Let's just call it A. X squared, what's the base polynomial for X squared? What's the base polynomial for X squared? It's just X, right? We don't care what power. This is the argument we did at the beginning of the day. If I have 1 over x to the n, I write it out. I have x squared, x cubed, x to the n. Yeah. All base polynomials are x and of degree 1. So numerators are constant. So it doesn't matter what power I have it just matters what is the thing that's being raised. So I'm raising x. Doesn't matter how many powers of x I have. And the reason is this calculation shows you, even though I have x squared and x cubed, I don't have to have a linear function above the x squared. I don't have to have a quadratic function above the x cubed because it doesn't gain me anything. When I combine these like this, notice I already have the most general polynomial I can of degree n minus 1. By putting in a higher degree polynomial for the x squared term and the x cubed term and so on, it doesn't give me any more generality in terms of what I can get. There's more than one way to get to the same polynomial. If you are trying to travel and trying to tell me how to get somewhere, what directions do you need to be able to give me? If you give me these directions, you can tell me precisely how to get to any place. What directions suffice to tell me how to move? Okay, good. Left and right, very useful. Can I get anywhere in the world by just going left and right? Up and down. So does everyone agree that if you give me left, right, up and down, you can get me to any spot in the world? What if you also added northeast, southwest? That might actually be convenient, right? Rather than going east and then north, it would be nice to just go northeast. Do you need to add it? Does it give you access to any more places than you would have had with just north, south, and east, west? No, it's the same thing here. I don't need to have a more complicated polynomial in the numerator. It's not going to give me anything better. I already get everything I need by having the polynomial 1 degree smaller than the denominator. Yes.
So say you had the denominator of like in parentheses squared minus 1 or plus 1.
Then you would need something linear up top. Because it's x squared plus 1, that's degree 2, so you want degree 1 upstairs. Yep. So when we go here, it's just going to be a over x. What about x squared? What would that be? It would just be b over x squared. And what about x plus 1? It would just be c. And so now what we need to do is we need to write 3x squared plus x minus 2 over x squared x plus 1. And now let's get a common denominator. So for the a over x, we have to multiply by x times x plus 1. So we have a x plus 1 plus b, we have to multiply that by x plus 1. And c, we have to multiply by x squared over x squared x plus 1. So 3x squared plus x minus 2 has to equal ax squared plus ax plus bx plus b plus cx squared. So the numerators have to be the same. And so I just get a common denominator. And now that I have a common denominator, I now just simplify things. So this is 3x squared plus x minus 2 equals a plus c x squared plus a plus bx plus b. And this must be true for all values of x. So what's the only way two polynomials can be the same for all values of x? So I have two polynomials, and I want them to be the same for every value of x. What must be the case if they're going to be the same for every value of x? So what should be true of these two polynomials? Must be equal for all x. So what's the only way they can be equal for all values of x? Sorry? So what does it mean for them to be the same? So we're basically saying that we can't write a polynomial two different ways. When you expand it out, what must be true? Do they have to have the same degree? Yeah, if the two polynomials didn't have the same degree, they couldn't be the same. If one is x to the fourth and one is x to the ninth, then as x gets really, really large, they're going to grow at different rates. So for two polynomials to be the same, they have to have the same degree. Right? What else has to be the same? The coefficients, all the coefficients have to be the same. If you take x equals 0, what does that immediately give you? -2 equals b. So if you have two polynomials that are equal, if you take x equals 0, the constant terms have to be the same. Okay? Remove the constant terms, divide by x, and now those polynomials must be the same. And now the constant term of that must be the same. Well, that was really just the linear term of the previous. So then you would get 1 has to be a plus b. Subtract that from both sides, divide by x, and now you get the constant term of what remains has to be the same. So the only way they can be true for all values is if all the coefficients are the same. The other way of seeing this is subtract one polynomial from the other. If it's not the 0 polynomial, you're in trouble because they're the same. They're supposed to take on the same values every single time. If it's not the 0 polynomial, it only will take on finitely many roots. So we get b is -2, we get a plus b is 1, and we get a plus c is 3. Okay, which is the easiest equation to solve? Yeah, give me that b equals -2. I'm going to start with that one. So we get b equals -2, then a plus b equals 1 becomes a minus 2 equals 1. So a equals 3. And then a plus c equals 3 becomes 3 plus c equals 3. So c equals 0. Sorry? So we had b is -2. It was a plus b equals 1. So a equals 3. And we get c equals 0. Do you think that this was done deliberately to make my life easy in terms of the problem I'm giving you? Or did I just get lucky? I will be honest. I got lucky. I absolutely got lucky. I just made up numbers. For small values, sometimes you can get lucky. So now we know what a, b, and c are. And now we can just do the integration. So we would have the integral was a equal to 3. We had 3 over x dx. And then b was -2. Right? So this is all that we have to do now. Okay, so this is 3 times the integral of 1 over x dx minus 2 integral x to the -2 dx. So this is 3 natural log of x minus 2 90. Oh, right. What function has derivative x to the -2? It'll be x to the -1, but then when I take the derivative of x to the -1, I get -1 x to the -2. So I need a negative sign. So my -2 becomes a +2. if you take the derivative of that, you will get negative 2 over x squared. And I can, of course, put in a plus capital C. Right? So it's important to remember that most of the time, the deeper you go in math, the less you use advanced mathematics. You use it very briefly, and then it becomes algebra. Lots and lots and lots of algebra. So the hardest part of this is doing the algebra to find out what is A, B, and C. And the more involved the denominator is, the worse it's going to be. If I give you, the integral of, say, f of x over, x cubed, x squared plus 1, x cubed plus 2 to the, I'll do squared, and I would have, it's going to be something over x plus something over x squared plus something over x cubed plus something over x squared plus 1 plus something over x cubed plus 2 plus something over x cubed plus 2 squared. And now let's try to just figure out what the stuff is. So the thing over x, what would that be? What degree would that be? So it would just be a constant. I'm going to use Greek letters because this way I don't have to worry about getting to the letter E, which I should never use as a constant. It's just going to be something over x. I'll do alpha. What about x squared? What would that be? Beta. Excellent. And the next one, x cubed. I'm sorry. We could do theta, but we might as well keep going in order. Alpha, beta, gamma. Oh, wait, no, alpha, beta. No, this is bad. Now you go. Alpha, beta, gamma. Yeah, it is gamma. Okay. I thought so, but I started to know delta myself. It is delta. Okay. So we go delta. And now what comes next? So next we're going to have, I'm sorry, it's gamma, but I wrote delta. So now things become more interesting. X squared plus 1, what is that going to be? What degree will that be? 1. So I'll write it maybe as A1x plus E0. What about the x cubed plus 2? What degree would that be? Quadratic. So we'll write that as B2x squared plus B1x plus E0. What about x cubed plus 2 squared? Also quadratic. The base polynomial is x cubed plus 2. I want 1 degree smaller than that. So that would be C2x squared plus C1x plus C0. And now if you look at it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, well, I now have 11 terms. So we have 11 coefficients. What's the degree of the polynomial over here? Polynomial has degree what? Has degree 11. How many coefficients does a polynomial degree 11 have? Nope. Let's take a quadratic. How many coefficients does a quadratic have? Ax squared plus bx plus c. Quadratic has how many coefficients? 3. So you might be a little bit worried, wait a minute, a polynomial has degree 11. This is 12 coefficients.
This is like C, is that x is 0?
Yes,
Oh,
yes. But remember, the numerator is 1 degree smaller than the denominator, at least, it might be more. So degree of f is less than 11. So f has 11 coefficients. So we expect that this should be doable. Some of the coefficients of f might be 0. If f is a polynomial of degree 3, you're going to have a lot of zeros in the beginning. That's okay. But when you look at this, this is a really nice, quick, simple calculation. I've got 11 coefficients on the right-hand side that I have to solve. When I expand it out, I'm going to get a massive mess. On the left-hand side, however, f has 11 coefficients. Some of them might be 0. So I'm going to have 11 equations involving 11 unknowns. They're all going to be linear equations. This is why you take a class like linear algebra. It's geared to solving problems like this. You put this in matrix form and you use the matrix magic. And you just manipulate through things. Otherwise, what you can do is you roll up your sleeves and you start substituting one variable in terms of another. I have got 11 equations. Let me solve for alpha in terms of everything else. And then I go through, and wherever I see an alpha, I replace it with everything else. Then I go through, and now I solve for beta in terms of, and I keep doing this until eventually I get one nightmarish equation involving one unknown. I solve that, and I go backwards and I build it. So this is the method of how you would do it. So again, now it all comes down to remembering what the integrals are of the standard functions. You have 1 over x to the m, 1 over x squared plus 1. We don't really have to remember 1 over x squared minus 1, because we can write that as x minus 1 times x plus 1. So there's really only 3 things you need to remember. Someday later in the semester, I will do an event of teaching people how to do the 2 by 2 by 2 Rubik's Cube. It takes about an hour to learn how to do it. And the difference between how I teach and how most people teach is I don't teach you how to solve the Rubik's Cube well. I teach you how to solve it. And there's an important difference. I am not trying to teach you the fastest way to do it. I'm trying to say, what is the bare minimum number of moves you need to learn in order to solve this? And some of the algorithms would be extremely efficient. It would be really nice if you knew how to do this. Like, it'd be really nice if we could move northeast. But if I can't move northeast, I can still get there by going east and north. And that means I only have to learn 2 types of movement. It's the same thing for stuff like this. There are certain things you just have to learn. My daughter loves telling the story of how she finally learned to tell the left from the right. It's when she was learning to solve the Rubik's Cube in kindergarten, and she needed to know, am I turning left or am I turning right? And now this was the first time in her life where it really mattered, getting left and right separated. And so she had to add that to her list of knowledge. Right now, you need to add to your list of knowledge the antiderivative of 1 over 1 plus x squared is arctangent. Before, it's just nice to know, but now if you're doing partial fractions, this is now up on a need-to-know basis. Because if I give you polynomial, I can always put a quadratic, hopefully, if I can't factor it, I can use vertex form and shift things and make it look like, and we saw how to do that transformation. So this is just one of the basics that you need to know. All right. So what I'm going to do now is I'm going to go back to this slide and recopy it here. Okay. And so are there any integrals on this page that people want to do? Let's just practice USub. That's what the people say USub. Anyone look particularly interested? Sure. And then in the interest of not being bored, I have not looked at any of these. So I have no idea how to do any of them. Okay. So when you see something like this, and again, the other reason I didn't want to look at any of these is I want to share my thought process. So when I'm looking at this, my first thought is, what should I choose for you? So possibilities. I could have 3 plus ln x. I could have 2 minus ln x. I could have ln x. I could have x. I could have 1 over x. I think those are the things that most naturally come to mind. Does anybody see anything else as a possible candidate? I'm just looking at what's in play for this problem. All the different factors. 3 plus ln x and 2 minus ln x. And those are potentially bad choices, because if I choose one of them, the other one's not going to be as nice. Although I could do 3 plus ln x is equal to like negative 2 minus ln x plus 5. Does that work? I think that works. So if I were to make 3 plus, if I would make 2 minus ln x my variable, I could actually write 3 plus ln x as just that variable plus 5. So it's not a huge deal to get from one to the other. So maybe that would work out. But the other thing that's going in my mind is, what's the derivative of the natural log of x? Is 1 over x, or the derivative of the natural log is dx over x. What does that suggest might be a good choice for you? Yeah, because we've got ln of x appearing in many places. And this way I don't really show favorites between the 3 plus ln x and the 2 minus ln x. Well, I can get around it. But it's nice not to show favorites. But I have a dx over x. And whenever you have a ln x, if you want to integrate a power of ln x, you want to have a 1 over x by it. So the integral of ln x to the 2022 1 over x dx. What does this equal? So can someone give me the antiderivative of the ln of x to the 2022 times 1 over x? Good. And then what would that coefficient be? Excellent. And that's exactly how you should do it. First, get the power right, and then fix. And when I take the derivative, I get 2023 comes down, cancels the denominator. Good. Ln of x to the 2022. And then I get a 1 over x from the chain. You could, of course, if you're having troubles with this, do u substitution. Let u equal ln of x. du is 1 over x dx. So you could do u substitution to solve this. But if I want to integrate a power of the natural log, it's very easy if I have a 1 over x next to it. If I don't have the 1 over x to it, it's not easy. And that's what we had to do, integration by parts. We played some tricks, and we got the natural log of x. Its integral is x log x minus x. But even more work, we get the integral of ln x squared. But it's much nicer when you have that 1 over x. Right, so continuing this problem, my intuition is to try u equals the natural log of x. So du dx equals 1 over x, or du equals 1 over x dx. And because I have a 1 over x dx, I'm not going to solve the dx in terms of du. I've got the 1 over x dx that I want to just substitute for. So our integral is going to just be the integral of 3 plus u squared 2 minus u over 4, and then dx over x is just du. Okay, now what do we do? So we can move the 1/4 outside. And what else should we do? Yeah, expand. So if we expand this, then we would get 9 plus 6u plus u squared times 2 minus u du. So it would be 1/4 integral. And then if we keep expanding, we would get 18 plus 12u plus 2u squared minus 9u minus 6u squared minus u cubed du. And I wrote it like that just so that's easy for me to quickly look and see how to combine terms. So then just be 1/4 the integral of 18 minus 3u minus 4u squared minus u cubed du. So it's 1/4. So what is the antiderivative of 18? 18x, except we're not using the letter x, we're using 18u. And then the next term, minus 3u, what function is the root of minus 3u? Yes, 3/2 u squared. I'll do the next one, minus 4/3 u cubed minus u to the 4th over 4. And now write ln of x. For u. Any questions about this problem? Everybody is comfortable with this problem? Got about 2 minutes left. So I emailed you earlier today the following problem. So this is from an exam that's basically the version of the SAT for grad school if you want to go to grad school in math. So suppose G is a continuous real value function such that 3x to the 5th plus 96 equals the integral from c to x of g of t dt. For each x and r, c is some constant. What is the value of c? So they give you a couple of answers. And the question is, how can you find it? So one possibility is to try to find what is the function g. Another one is, can I remember that the point of this problem is not to find g, it's just to find what value of c works. This has to hold for all values of x. What might be a really good value of x to try, where the integral is going to be really easy to do? Nope, it's not 0. 0 is not a bad try. It's not 0. Not once. Look at this integral. I'm integrating from c to x. What choice of x will make this integral really easy to evaluate? Nope. I'm not telling you what the function g is. There's only one value of x, where if you put that in, you will know exactly what this integral is. You have to tell me what value of x to take. I'm integrating from c to x of g of t dt. I don't know what the function g is, but if you give me one special value of x, I know what the integral is. Oh, 2. When you integrate, it's going to be the antiderivative at x minus the antiderivative at c. What choice of x will have the right-hand side easy to evaluate? What do you think x should depend on? C, x should depend on c. Can you give me a good choice of x as a function of c, where the integral from c to x would be very easy to compute? Nope. C. It works both ways. I was actually thinking C. When you take x equals c, what is the value of the integral? 0, c. So you would get 3c to the 5th plus 96 equals 0. Therefore, c to the 5th equals negative 96 over 3. And so what's 96 over 3? 32. -32, so C equals -2. So for a problem like this, you don't actually have to find the function. Always ask yourself, is there a special case? This is similar to what we're doing today with partial fractions. If it's going to be true for all values of x, let's take x equals 0. It's always trying to figure out what is the good value to look at. All right, this is a good place to stop. Have a good rest of the day.